Dear students, in this lecture we will find out the solution of the wave equation derivative 2 y upon derivative t2 is equal to c square derivative 2 y upon derivative x2, where c square is equal to t upon m, which we have already discussed in my previous classes, and we will try to find out the solution of this wave equation by using method of separation of variables. What is given here? Given this is the wave equation derivative 2 y upon derivative t2 is equal to c square derivative y upon derivative x2, and which is this wave equation is abide by the condition y equal to 0 when x equal to L. Here in my first class, as I already told you, the string is stretched between 2 points O and A, and this length is L. Okay, here x equal to 0, y equal to 0, here x equal to 0, y equal to 0, x equal to L. Y equal to 0 when x equal to L, when x equal to 0, and y equal to 0 when x is equal to L. Here these two conditions should be satisfied by every value of t, and if the string is made to vibrate by pulling it into curve y equal to fx and then releasing it, the initial conditions are y equal to fx when t equal to 0 and derivative y upon derivative t equal to 0 when t equal to 0. Any wave equation of this form, derivative 2 y upon derivative 2 is equal to c square derivative 2 y upon derivative x2, is abide by these boundary conditions: y equal to 0 when x equal to 0, y equal to 0 when x equal to L. Here is the length of the string, and y equal to fx when t equal to 0, and derivative y upon derivative is equal to 0 when t equal to 0. Suppose this is the equation number 1. Now in method of separation of variable, we assume its solution, which is made up of with product of dependent function of independent variables. That is, here we have y as a dependent variable and x and t are two independent variable, means product of two function of two independent variable x into t, where capital X is a function of x alone and capital T is a function of t alone. And suppose this is the equation number 2. Now we find out these two terms, derivative y upon derivative x2 and derivative y upon derivative t2, with the help of this assumed solution y equal to x2 or equation number 2. Now first we differentiate 2 partially with respect to t, means what is the value of derivative y upon derivative? Here x and t are function of x and t. Okay, x is a function of small x, t is a function of small t. Now its derivative we represent by dashes. dy upon dt is x t dash, and second order derivative with respect to t, assuming function of x as a constant, it will be x t double dash. Now differentiating to partially with respect to x, derivative y upon derivative x equal to x dash t, and derivative y upon derivative x2 equal to x double dash t. Now substituting, putting the values of derivative y upon derivative 2 and derivative y upon derivative x2 in equation 1, we have what we have derivative y upon derivative 2, that is x t double dash is equal to c square x double dash t. Next we have to separate the variables. Now we separate the variable. We write down all terms of capital X and function of x in one side and all terms of t other side. That is, we can write down this as a x double dash upon x is equal to 1 upon c square t double dash upon t. And let us assume each side equal to an arbitrary constant k, and suppose this is our equation number 3. Okay, now we have two relation. Number 1, x double dash x upon x is equal to k, and number 2, t double dash upon t is equal to k. That is x double dash x minus kx is equal to 0, and here we get t double dash minus kt equal to 0. These are two ordinary differential equation, two second order ordinary differential equation with constant coefficients. Also we can write down this as a in other form, that is this will be d2x upon dx2 minus kx equal to 0, and this is the second d2t upon dt2 minus kt equal to 0. This is an ordinary second order differential equation with constant coefficients for the dependent variable capital X and independent variable small x, and this is an ordinary differential equation with constant coefficient for dependent variable t and independent variable t. Okay, now we have to solve this equation. Now here 4 cases maybe arises. Okay, it depends on k, what we choose k. If k equal to p square, if k is positive, then what will be the solution of this differential equation? If k is negative, then what will be the solution of this equation? And if k equal to 0, then what will be the solution of this differential equation? Okay, now 3 cases arises, and suppose these are the set of 2 equations. This is equation number 4. Now we take case number 1. Case first, when k is positive, and suppose equal to positive means this is equal to p square. We can take this term will always be positive. When k is positive, we can choose this as a p square, because p square can never be negative term. Then what we get here? Here we have differential equation in this form: d2x upon dx2 minus p square x equal to 0, and here we have d2t upon dt2 minus p square t equal to 0. Here auxiliary equation is m1 square minus p square is equal to 0, and here auxiliary equation is m2 square minus p square is equal to 0. Here we have roots m1 equal to plus minus p, and here also we have root m2 equal to plus minus p. Here m1, meaning of m1 is d upon dx, and here meaning of m2 is d upon dt. What is the solution here? Here particular integral will be 0 in both the cases, because right hand side is 0, and here complementary function will be the complete integral, means solution of this, here x equal to, this will be c1 e to the power px plus c2 e to the power minus px, because here we have independent variable x, and here capital T. Solution means we have to find the value of capital T in terms of independent T, this small t, and here we have c3 e to the power, oh sorry, this is what we have here, t, this here we have c square term, one term we have left, this will be kc square. Okay, here we have also c square, and this will be p square c square, p square c square, and this is plus minus pc. Okay, means here we have c3 e to the power pct plus c4 e to the power minus pct. Okay, and what is the solution? Now from equation 1, equation 2, we know that solution is y equal to xt, that is y, which is a function of x and t, is equal to product of these two, that is c1 e to the power px plus c2 e to the power minus px into c3 e to the power pct plus c4 e to the power minus pct. Okay, this is the solution when k is positive. Okay, now we come to the second case, when k is negative. When k is negative, and suppose this k is equal to minus p square, and this p square term, we can say this will be always negative term. Okay, say this k equal to minus p square. Now what we have? Differential equation. Now from equation 4, we have two differential equation. Number 1, derivative by 2x upon derivative by x2 plus p square this is c square. Okay, here we have this term c square. P square x is equal to 0, and second equation we get here t2t upon dt2 plus p square c square t is equal to 0. Okay, now what will be the auxiliary equation here? Here auxiliary equation are, in first case m1 square plus p square equal to 0, and in second case m2 square plus p square c square equal to 0. Now we find out roots of this auxiliary equation. Here we have m1 equal to plus minus ip, and here we have roots m2 equal to plus minus IPC plus minus IPC. Now here solution, here also right hand side is 0 in this differential equation, means particular integral will be 0. Complete solution of this equation is complementary function plus particular integral, but here right hand side 0, that's why particular integral will be 0, means complementary function will be the complete solution, and complete solution means value of capital X equal to here C1, here imaginary root. If alpha plus minus I beta we are roots of this auxiliary equation, then we know the solution is e to the power alpha x c1 cos beta x plus c2 sin beta x. Here alpha part is 0, we have only ip, means here we have c1 cos px plus c2 sin px, and in second part capital T, here also right hand side is 0, means particular integral will be 0. Here complementary function will be the complete in solution of this differential equation, means capital T equal to CA plus PI, but PI is 0. So complementary function will be the complete integral here, means capital T equal to, here we choose another constant C3 cos PCT plus C4 sin PCT. Now from equation 2, what is equation 2? Y, which is a function of xt, is equal to x into t, that is y xt. What we have when k is negative? X means here we have c1 cos px plus c2 sin px into c3 cos PCT plus C4 sin PCT. Okay, this is the solution of the given partial differential equation when k is negative. Okay, now we come to the third case. When k is equal to 0. Okay, when k is equal to 0, now from equation 4, if we put k equal to 0 in equation 4, here what we get here, when if k equal to 0, from equation 4 we get here we have number 1 d2 capital X upon dx2 is equal to 0 and d2t upon dt2 is equal to 0. Okay. Here, what are the roots? Now, when we integrate this, what we get here? Dx upon dx is equal to c1 and dt upon dt equal to, suppose here we have c3. Okay. Now, for getting this solution, we integrate, we get this term. Again, we integrate this, we get here c1x and we add another constant, and here we get c3t plus another constant c4. Okay. Now from equation 2, that is yxt is equal to x into t. Now putting the value of capital X and capital T in equation 2, we get yxt is equal to c1x plus c2 and c3t plus c4. Okay, and this is the solution of the given wave equation for all the three conditions. When k is positive, we have this solution. What we have here? Now we have solution when k equal to 0. What are the solutions? When k equal to, when k greater than 0. When k greater than 0, k is positive, that is k is positive. We have this solution. Y equal to xt c1 e to the power px plus c2 e to the power minus px and c3 e to the power pct plus c4 e to the power minus pct. And when k less than 0, k less than 0, that is k is negative, we have solution yxt equal to c1 cos px plus c2 sin px into c3 cos pct plus c4 sin pct. And when k equal to 0, we have the solution of this wave equation yxt is equal to c1x plus c2 and c3x plus c4. Okay, we have three kind of solution for this wave equation. From these three solution, we have to choose that solution which is consistent with the physical nature of the problem. Here we are discussing the wave equations. Okay, it should be our solution must be related with the physical nature of the problem. Here we are dealing problems on vibrations of stressed string. Here we have vibrations. Okay, vibration means when we have this kind of vibration, this come up and down like this, means this is, here we have a periodic function. It's nature of the problem. Here we have periodic type of function. Since we are dealing with the problems on vibration, here y must be a periodic function of x and t. Here x and t are two independent variables. Therefore, the solution must involve the trigonometric term. That's why for purpose of this vibration of stress string, we use only this solution because it is having trigonometric term. It should be, our solution must be related with the physical nature of the problem. That's why we use here trigonometric terms. Okay. So it should be involved trigonometric term. In all the vibration problem of stressed string, we will use this solution only. Okay. Directly we can use this solution, or we can find out with the help of wave equation by the method of separation of variable. Now, important, the only solution, that is, we can say, that the only solution of the wave equation and it correspond to k equal to minus p square is yxt is equal to c1 cos px plus c2 sin px and c3 cos pct plus c4 sin pct. Okay. Now we should apply the boundary conditions. Now we have to apply here boundary conditions. What are the boundary conditions? Now we apply the boundary conditions. Here wave equation is abide by this boundary condition. When y equal to 0, when x is equal to 0, okay, y equal to 0 when x is equal to L, because L is the length of the string, okay, which I told you in my first class. Here length of the string OA and this length is L. And y equal to fx when the time t equal to 0. Here function, here this is the function, here this is the function. Suppose this is the shape of the curve. At the time t equal to 0, where is no display, no vibration, where is in equilibrium position. Here y function है y equal to fx when t equal to 0. And when we vibrate this means, and when we displace from its equilibrium position, okay, the function will be changes in this y, and at the time t, this changes of y at the time t will represent d over y upon d over t. Okay, now it is d over y upon d over t, and at time t equal to 0, this d over y upon d over t will be 0. Now these are the boundary condition. Now one by one we apply this boundary condition. First condition, when y equal to 0, first condition, y equal to 0 when x equal to 0. This is our first boundary condition, y equal to 0 when x is equal to 0. Now y equal to 0, suppose this is the equation number. Now we assume this, suppose this is the equation number 5. Suppose this is the equation number 5. Okay. Now y equal to 0 when x is equal to 0. Here we put y equal to 0, 0 and x is equal to 0. That is C1 when x equal to 0, cos 0 is 1 plus C2 sin 0 is 0, and here we have the same term C3 cos PCT plus C4 sin PCT. Okay, that is C1 C3 cos PCT plus C4 sin PCT equal to 0, and we know that this term can never be equal to 0. Okay, means this term can never be equal to 0, means definitely this constant will be equal to 0. Now we put this constant, value of this constant in our equation number 5. Now we put this constant C1 in equation number 5. What we get here? Yxt, y which is a function of xt, and we put here C1 equal to 0. What we get here? C2 sin px into C3 cos pct plus C4 sin PCT. Okay. Now we apply the second condition, and suppose this is the equation number, and suppose this is the equation number 6. Okay. Now what is the second boundary condition? Here second boundary condition is y equal to 0 when x is equal to L. Second boundary condition is y equal to 0 when x equal to L. Now applying this boundary condition in equation number 6. Okay. Now we apply this boundary condition in equation 6, that is from equation 6 we have to apply this boundary condition, y equal to 0 and x is equal to L, that is C2 sin PL, and here we have C3 cos PCT plus C4 sin PCT. Okay. Now what we have here? Here this term can never be equal to 0, means what we equal to 0, here we equal to 0, this term and this term never equal to 0, means we have sin PL is equal to 0, or we can say sin PL is equal to sin n pi, for where n is positive integer. So means n pi means here n is positive, means this will be 0, that is we have PL equal to n pi on solving, that is P equal to n pi upon L. Now putting this value in equation 6, from equation 6, substituting this value of P in this equation, what we get? yxt equal to c2 sine n pi x upon L into c3 cos n pi ct upon L plus c4 sine n pi ct upon L. Okay. Now suppose this is our equation number 7. Now what are the other boundary condition? Other boundary condition are y equal to fx when t equal to 0 and diver by upon diver t equal to 0 when t equal to 0. Now we apply these other two boundary condition and we see the what will be the impact on solution of these two conditions. Now we apply another condition. What is the another condition? Y equal to fx when t equal to 0. Now we apply this boundary condition on equation number 7. So what we get here when we apply this condition, that is y equal to fx is equal to when t equal to 0. T equal to 0 means what we have here? C2. What we have when t equal to 0? Sin 0 will be 0, cos 0 is 1. We get here C2 into C3, C2 into C3 sin n pi x upon L. Okay. For the most general solution, what we can take here? Here we can choose this fx equal to summation n equal to 1 to infinity an sin n pi x upon L. an sin n pi x upon L. Okay. And suppose this is the equation number 8 मान लीजिए. And diver, what is the another boundary condition? Diver y upon diver t equal to 0 when t is equal to 0. And what is diver y upon diver t? Now we differentiate diver y upon diver t. Now differentiating this partially with respect to t. What we get here? C2 sin n pi x upon L, and here when we are differentiating with respect to t, here we get n pi c upon L. What is the differentiation of cos? Differentiation of cos is sin n pi c t upon L. Okay. Differentiation of sin is differentiation of cos is minus sin, and what we have here? Here we have also C3 term, C3 plus C4, and what is the differentiation of this? L upon n pi c, and this is cos n pi c t upon L. Okay. Now this equal to 0 when t equal to 0. When we put t equal to 0, what we get here? C2 sin n pi x upon L. C2 sin n pi x upon L. This is n pi x upon L. And what we have here? When t is equal to 0. What we have here? When t equal to 0, this term will be 0. Here we have C4, not L upon, this will be, here we write, this term will be n pi c upon L. Here we are differentiating, not integrating. If we are integrating, then we divide this. So means this term will be n pi c upon L. Okay, please correct this term. Means C4 n pi c upon L, and cos 0 is 1. Okay, that is what we have here. Most generalized, what we can write here, dever y upon dever t, dever y upon dever t, that is in general form, n equal to 1 to infinity, taking C2 C4 is equal to Bn. This is n pi c upon L sine n pi x upon L, and suppose this is our equation number 9. No. In this equation, number 8, in equation 8, since equation 8 represent Fourier series for the function fx, we have an is equal to, from equation 8, means this equation, an is equal to 2 upon L, 0 to L, fx sine n pi x upon L dx. And suppose this is the equation number 10. Okay, from equation 9, here from this equation, here dever y upon dever t equal to 0, means Bn equal to 0 for all n, that is, hence equation equation 7 reduces to what is equation 7? This is yxt, c2 sin n pi x upon L, c3 cos n pi ct upon L plus c4 sin n pi ct upon L. That is yxt is equal to and we can take this in most general form. Here we have only this term, sine, this term will be 0, means summation n equal to 1 to infinity, and here this term will be 0, an sin n pi x upon L. This means here we have summation n equal to 1 to infinity an cos n pi ct upon L into sin n pi x upon L. N pi x upon L. Okay, where an is given by equation number 10. This an, we find out an in this way. Okay, and we get only one term here, and suppose here C2 into C3 equal to an, sorry, C2 into C4 is equal to an, and C2 into C3 we assume as Bn, and Bn will be 0, means this term will be 0, here this term will be 0, and we get only this term, means C2 into C4 cos n pi ct upon L and sin n pi x upon L, and assuming this C2 into C4 is equal to an, and this an can be find out by using this formula. Okay, and this an can be calculated by using equation 2, and which is the final solution of given this wave equation. Okay, I think this lecture is clear to all of you. If you have any queries regarding this solution of this one-dimensional wave equation, then you can comment on comment box. If you feel this lecture is helpful for you, then you please like and subscribe this channel, and also press bell icon for getting further notifications about my videos. Okay, thank you very much. Have a nice day, and Bharat Mata ki Jai.